And of course, the double bond is somewhere in between the two. So we go from the longest to the shortest. So the length of the bond decreases as the number of electron pairs increases. And hopefully, at this point, you guys are familiar with this bonding here. In here, we have 2 electrons. So Q is equal to how many? Each electron is -1. So Q is equal to -2. Okay? What's Q equal to in a double bond? Q is -4. And in a triple bond? Q is equal to -6. And because Coulombic attraction is proportional to Q, therefore, the bond pulls the nuclei closer. The electrons pull the nuclei closer to each other. Or I should say 6 electrons pull the nuclei. Why will this not erase? There we go. To each other. Or maybe I should say closest. 6 electrons pull the nuclei closest to each other. Therefore, N triple bond N is the shortest. Is that good? Does that make sense? Is that something that you already knew probably? Yeah, okay. Good stuff. Now, you should have a piece of paper out in front of you because we're going to draw a few Lewis structures today. And we're going to start on a blank piece of paper somewhere. Go grab yourself a blank piece of paper. There's some free paper back there. Go help yourself. We are going to draw the Lewis structure for O3. So that's what you guys are going to do now. And if you've forgotten your steps, I'm going to write them over here. Valence electrons. What else do we do? So start with your first 4 steps. And if you've forgotten, you're going to count your valence electrons, draw your skeleton structure, add lone pairs, and then count your electrons. So step 1, count your valence electrons. How many valence electrons, everyone? 18, because we have 3 oxygens in group 16, so it has 6. Skeleton structure, there's nothing else to do. Put them in a line. There's only 3 of them. Add lone pairs until all atoms have 8 electrons, so that's done here. Whoops. And then we count the electrons in that structure. We have 8 lone pairs and 2 bonds gives us 20 electrons. What are we comparing that 20 electrons to? We are comparing it to the 18. Does it match? No. If you have too many electrons, you're going to erase lone pairs. How many pairs too many do we have? We have 1 pair too many, 2 electrons or 1 pair too many. So you're going to erase 1 lone pair, and who should you erase it from? From the central atom. So that's going to now look like OOO. And then we've erased our lone pair from the central atom. It was up here, but now it's gone. Is that a good structure? What's wrong with that structure? Or is it a good structure? Pardon me? The central O only has 6 electrons. 2, 4, 6. That's no good, right? It needs to have 8. So how about I just put a pair there? I just got rid of those. That would be silly. Okay, so let's get rid of those. Remember, what we have to do is we have to turn lone pairs into bonding pairs. How many lone pairs? 1, because we had a 1. We're going to turn 1 lone pair into 1 bonding pair. So we're going to take this and we're going to move it in. Would it matter which one I moved? No. I'm going to give you a couple of options, though, just to show you where you could go wrong. Okay. What if you did this? Would that be okay? No, why not? Yeah, we haven't solved our problem, have we, right? We would still have, this guy over here would have, oh my gosh, 2, 4, 6, 8, 10 electrons. And this guy would still only have 2, 4, 6 electrons. And the oxygen on the right, I guess, would be okay, but he would be the only one, right? So that's no good. That's terrible. Yes? So you have to make sure that the one you're moving actually solves the problem. Okay, so we're going to move this one in. So now we have oxygen, bond, bond, oxygen, whoops. And it doesn't really matter where you put these two electrons, these two lone pairs. You can put them at the top and the bottom, the top and the left and the bottom, the left and the top, whatever you like. Or if you want to put them on a trigonal planar geometry, you can do that too. Okay? Ooh. Okay. Now, we know that this is a correct Lewis structure. What step is it? Is it step 6? Let's go see. Nope, not that one. There we go. Draw the skeleton structure, add lone pairs, count and check. Oh, I've not got it. What is wrong with me? Oh, there we go. We ask, is it an ion? Does it have resonance structures? And check that everybody has 8 electrons. Okay, so let's go back to where we were. Step 6, is it an ion? No. So we don't have to do brackets and a charge. Step number 7, are there resonance structures? Resonance structures means you have a double bond or a triple bond that can move. You have a movable pi bond. Yes? Do you have a pi bond that can move? Do we? Yeah. Okay. So in order for this thing to move, usually what we do is, in order to show that movement, we would show a lone pair moving in to form a bond. And then at that point, this poor oxygen in the middle would have 2, 4, 6, 8, 10 electrons. That's no good, right? So we would then take this bond and move it outward. You do not need to show that process, okay? I'm just showing it to you because that's how the bond moves. It's not like the bond jumps and then the electrons, jump over to the other side, right? They all kind of go like a set of dominoes. Bunk, 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 bunk. Yeah? How you would draw your resonance structures is you would draw your first resonance structure, which has 2 lone pairs and the double bond. And how do you draw the other one? You would have oxygen in the middle still. Where does the double bond go? On the right. How many lone pairs on the right-hand oxygen? 2. What kind of bond on the left? Single bond. O. And then we have how many lone pairs? 3. 1, 2, 3. And in order to show that they are going back and forth between the two, what do we need to draw? A 2-way arrow. And I would put a box around this and say, there we are. Answer. Is good? Yes? No, you can put the electrons on the bottom or you can put the electrons on the top. So your central O, it could also look like that instead. Okay? Doesn't matter. Now, just before we carry on, what shape is O3? And what is the bond angle in O3? It's not linear. Have a little chat about that. It's not linear. Triangle is wrong. Don't draw triangles if you have a choice. Okay? Just draw things, don't make things cyclical unless you don't have a choice. Okay? Because most things are not cyclical.
Well, like I was confused because I always see like oxygen with 2 bonds. Now it's with 3 bonds.
I know. That's because ozone's weird. Yeah. Okay. What shape is it? It's bent because we have a lone pair here. So how many electron domains do we have? 3 electron domains. Right? And then they push away from each other as much as possible. So what shape would that be? It would really look like this. And lone pairs are more repulsive than bonding pairs, than a single bond. So normally what we would have is we would have 120, 120, 120, yes? But if this is a lone pair, then this gets pushed away. And this gets pushed away. And so this is now going to be less than 120. It's all of us, like if it's at 120, all of a sudden they get pushed more. And so they're like, ooh, squish. So you guys can tell me how good a job I do of this. Is this a 120 degrees right now, how I'm holding my arms? No? How about that? Down?
Yeah.
There?
Yeah.
Down.
A little bit up. A little bit up. Okay.
Yeah.
Is that 120?
Yeah.
Okay, so this is what happens if each of my hands and my head are atoms. Yes?
Yeah.
Okay. Now imagine my head has become a lone pair. It is more repulsive. What do my arms do?
Yeah.
So what is this angle here? Less than 120. Okay? And the angle between the lone pair and the bond is more than 120, but we're never looking at a lone pair bond angle. We're always looking at the angle between 2 bonds. Okay? Yeah. So what shape is it? It is bent. And what is the bond angle? Less than 120 degrees. Is this a polar molecule or a non-polar molecule? Well, that's actually a good question. If indeed it did go back and forth between these two, you would have a more negative charge over here, right? Because you've got more lone pairs, and then you would have a more negative charge over here. However, that's not what actually happens. So we're going to go back here and we're going to take a look at what really happens in O3. Okay, so here's O3. If we look at this, if this is the correct structure, what could you say about bond length A and bond length B? Bond length A would be longer than B. Does that make sense? Okay. Now, turns out, when you measure the bond lengths, they are not different. They are the same. So that means that this must be wrong. I mean, it's kind of right, but it's wrong. Okay? And this is where we come to that's where we go back and forth. Okay, so we're going back and forth. Those are our resonance structures, two resonance structures. But what this actually tells us, because we can't draw an average of those two structures, this says these two structures are averaged. That's what those back and forth diagrams are telling you. So it's not an accurate representation of what is, but it's trying to tell you that those are averaged. Okay? So they really don't have a bond on one side and a bond on the other side. What really happens, did I move that too quickly? Are we good? It's like if you have blue and yellow, and you go back and forth between blue, yellow, blue, yellow, blue, yellow, blue, yellow, blue, yellow. But really, what do you have? You have green. Okay? So rather than going back and forth between double bond, double bond, double bond, double bond, back, we get a structure where it's the same on both sides. It is symmetrical. The bond length here is the same as the bond length. Okay? Yes? You can. Yes, you can have a triple bond, but it's less usual. You can, but it just doesn't happen as much. Usually what you have is you have a double bond alternating with a single bond. Okay? But it has to be, like, let's just say that we had Are you going to be able to get resonance there? No, because like if we had like, let's just say there was an oxygen, I don't know. Like you can't, it wouldn't move. I don't know what I'm drawing there. Never mind, pretend I didn't draw that. Okay? Yeah, we'll get to some better examples later on. Okay, so basically what we've got is the bond lengths are the same. And if we have, on average,
So
on the left-hand side, we have 2 bonds and 1 bonds. What's the average of 2 and 1? 1.5. So that is really a 1 and a half bond.
So if one is technically 1, the other one's 2, they would like look at it, average out to 1.5 on the side.
Yeah. So bond A is the average of
On A.
1 bond and 2 bonds equals 2 plus 1 divided by 2 is 1.5. So the bond order is 1.5. Yes?
But why we draw the structures, why don't we just draw the one in between and mark to
I would like you to show me how you draw the one in between and show the correct number of lone pairs. Try it.
like just draw one line and a puff line next to it.
Okay, hang on. Bond order is 1.5. Yeah? Because a single bond is bond order 1, a double bond is bond order 2, and so if you have 1.5, then the bond order is 1.5. I'm just going to get to that in a second. I'm just going to let people write things down here, and then we'll move the screen and provide some drawing room. Yes? Pardon me? I think we're going to come across an example a little bit later, okay? So you would probably have a triple flipping to 2 doubles, like you'd have a single triple, and then you'd go to having 2 doubles instead, okay? Okay, now let's pop on over here and let's look at oxygen. Actually. So we'll show our half bond as a dashed line, okay? We'll show our half bond as a dashed line. The dashed line here is a half bond. Okay, what is really happening is that the pi bond is delocalized over the entire area.
So is it also structure?
Kind of, but you wouldn't draw it this way on the AP exam because I don't think they ever ask for you to do this. Okay, the pi bond. Yeah. So on the AP exam, if they ask you to draw ozone, you're going to draw one structure with the double bond over here, and then you're going to draw the other structure with the double bond over here, and then you're going to draw the 2 arrows in between. What does it mean to be delocalized?
It's not at one place.
Not in one place. Now, where do I draw my lone pairs? I have one lone pair here. Where do I draw the rest of them? Because one of them has 2 and one of them has 3. Where do I put the 2 and where do I put the 3?
Just put 2 and 2 and 2 and 2. Why can't we do that?
Because then I don't have the right number of electrons. That's the right number of electrons. So where do I put the 2 and where do I put the 3 if I draw it like that? You can't. That's why, as a chemist, you draw it like, where is it? Oh, come back here. You draw it like this. And as a chemist, you know that that means that it's a blend of the 2. Yes? Just like when I write a chemical formula. Let's say I wrote CuCl2. As a chemist, you should know that the charge on the copper is 2+, even though I don't write 2+ anywhere there. Do you know what I mean? You're inferring it from the information I've given you. Yeah? So you have to, as a chemist, you have to infer that when we write the resonance structures like this, that we actually have that blended structure. Because there is no way to write the lone pairs. You cannot draw a true Lewis structure for a structure that has resonance. You can't do it. It's not possible. The Lewis model doesn't work well for that. You would need a different model. And there are different models, but just not the Lewis structure. Yeah? Yeah.
So, where are the low?
I don't know. There's around somewhere. I don't worry about it too much because I don't need to do that. You can go ask a third-year professor or something. We might find out during valence bond theory. I'll look, but it's not being tested, so we're going to try and cut out a few things that are not being tested. All right. Okay, so there we go. Give it some thought. The OO bonds in ozone are often described as 1.5 bonds. Is this description consistent with the idea of resonance? Well, yes. Okay. There we go. Now, let's do nitrate, NO3. So on your paper, NO3 minus. Draw a structure for that. Did we all get up to here okay? Okay. What do we do with that one lone pair too many? We erase one lone pair from the central atom. I'm just going to put LP for lone pair. There it goes. Bye-bye. Turn how many lone pairs? One lone pair into a bonding pair. Pick any one. I picked the one on the right. You could pick the one on the left or the bottom. Doesn't matter. Did you all get a structure that looks like this or had the double bond in a different position? Are we good with that? Okay. Now the question is, what's step 6? Is it an ion? Yes, it is. So what do we need? Brackets and charge. And then step 7 is, do we have resonance? Do we have resonance? Yes, we do. So you're going to draw how many more structures? 2 more for a total of 3. Yes. Yes. It doesn't have to be at the top and the bottom. It could be at the side and the bottom or the side and the top. Okay, these ones could be, or they could be like diagonal. Totally fine, okay? So for example, here, I'm just going to draw them like that just to show you what that would look like, okay? I would probably be consistent in how I drew them from structure to structure, but honestly, it doesn't matter too much. Do you know what I mean? Yeah. So once you've got that and you've got your arrows in between, you should double check that everybody has 8 electrons. Does everybody have 8 electrons? Do you have the correct total number of electrons? Yes, we do. Okay. Honestly, like the first while you are doing Lewis structures, people tend to do silly things like have the wrong number of electrons or have an atom that does not have 8. Other than, who are the exceptions who don't need 8? B-ball and hydrogen. How many does hydrogen need? 2. How many does beryllium need? 4. How many does boron need? 6. And aluminum? 6. All right, what is the shape of this nitrate ion? Is it T-shaped? Sasha's shaking her head back there. No, it's not. No, what is it? How many electron domains are there around the nitrogen? Nitrogen has 1, 2, 3 electron domains. And if it has 3 electron domains, what shape do we have? Trigonal planar, because there's no lone pairs. Okay? Now, if I actually had a structure that was like this, double bonds are more repulsive than single bonds because there's more electrons in them. So if I actually have a double bond, then this bond angle would be less than 120, and these two would be greater than 120. However, do I actually have a double bond? Yes? Yeah, the bond order is 1.3 repeater. Okay, or you can say 1 1/3. Okay, because if we look at, say, let's call this bond A, this one on the right here, A. Bond A, we have 1 bond, we have 2 bonds, we have 1 bond. So that's 3 different situations. So we put 1 plus 2 plus 1 divided by 3 is 4/3, which is 1.333. And you can just put a 1.33, or you can say 1 1/3. That is our bond order. And if that is the case, what can you say about the lengths of the bonds in NO3? Are they different or are they the same?
Same.
They're all the same. All the bonds in NO3 are the same strength and the same length. And so what would our bond angle be if all of those bonds are all 1.3? What would our actual bond angles be? 120. Okay, because we don't actually have a double bond. What we actually have is NO, O, O. And you could draw it like this. And when we draw something like that, we just leave off the lone pairs because we cannot accurately depict the lone pairs. Okay? There's a 1.33, 1.33 bond order. 1.33. And this angle here is 120 degrees. And this is 120 degrees, and this is 120 degrees. Yay. How are we feeling about that? Yes? It's exactly 120 because all the bonds actually contain the same amount of electrons. It would only be if we had an actual double bond that's more repulsive, we would get that extra repulsion, right? But we don't have a real double bond. We have 3 equivalent 1 1/3 bonds. Is good? Yep. So it's just 120. Yeah. Which has a shorter sulfur oxygen bond, SO3 or SO3 2 minus? SO3 2 minus or SO3 neutral? What are you going to have to do to solve that problem? Draw the Lewis structures for both. See how quickly you can do it. Four, 5, 6, 7, 8, 9, 10. Yep. Huh. It's exhausting, isn't it? Okay, that's what you should have gotten for your two structures. The one in the brackets on the left is your SO3 2-, and it has no double bonds. The SO3 with no 2- has one double bond. So what is the bond order here? In SO3 2-, it is 1 for all of them. Yes? But here, the SO bond order is how much? 1.33. So which one has the shorter bond? The higher one has the shorter bond. Yeah. Okay. Okay, those bonds in SO3, not too negative, sulfur trioxide, are going to be shorter and stronger. Does that make sense?
So bond order is just the number of bonds.
So if you've got resonance structures, just pick one of the bonds that you want to look at. Just say, I'm going to pick this one here. It is double bond 1/3 of the time. It is single bond 1/3 of the time, and single bond 1/3 of the time, right? So you're averaging 1 and 1 and 2, and you're averaging it over 3 structures. So you have 1 plus 1 plus 2 over 3 structures gives you 1.33. Yeah? Now, question. What is the shape of the neutral molecule? What is the shape of the neutral molecule, the one on the right? Trigonal pyramidal. Trigonal pyramidal? Trigonal planar. Yeah. Trigonal planar. What is the shape of the ion? That one is trigonal pyramidal.
Yeah.
Yeah?
Wait, so the non-ion is the planar and the ion one is
Yeah. So this one is trigonal planar. That one is trigonal pyramidal. What is our bond angle in the one on the right, the neutral molecule? 120 degrees. What is our bond angle in SO3 2-? Remember, now we have a lone pair. So what we've got is let's see. Imagine that my head is like the part sticking up. That is my lone pair, yes? And then we have my body. That's one of the, here, I gotta lean, okay? Then we go like this, like I'm like a little tripod, yes? My body is one of the limbs of the tripod. My head is sticking straight up. Are we good? Yes? Okay. So what happens if this becomes a lone pair instead of a molecule? These things all go swoosh. Yes? Swoosh, swoosh. Right? Because the lone pair pushes them away. And so what does the bond angle become? Less than 1/0. This is the weird one. 109.5. You don't have to tell us how much less. Okay, it's just less than 109.5. Huh? What?
Like you're supposed to like.
Okay, so if the bond angle is this angle here, yes?
Yeah.
And if it goes, whoop,
Yeah, so that's
that got smaller. So it's less than 109.5.
You were doing it like, maybe I was doing it off.
Huh? I don't know. It's hard for me to, like, got to have my head up and leaning forward. And anyway. How are we feeling about all of this? All right. So you guys can now, if you want to, you can do the practice exercise HCO3, or you can, actually, no, we should really cover this. We should really cover benzene.
Oh no.
Here's benzene. Benzene is a ring structure, okay? Benzene. Benzene has how many carbons? 6 carbons. And what do you notice about the double and single bonds in the ring?
Every other one.
Every other bond is a double bond in the ring. Now, benzene is a hugely, hugely, hugely important organic compound. What's around the outside of the benzene? Hydrogens, all hydrogens. H, 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 H. Now, the reason you can have resonance is if this double bond moves here, that would give, like, let's say I'm going to draw it here for a second. Let's say I drew that there. How many bonds would that give the right-hand carbon? That would give it 1, 2, 3, 4, 5 bonds. Yes, that's no good, correct? So we wouldn't want to have that. So what would have to happen? The next bond would have to get kicked over, and then that would cause a problem for this carbon, and so this bond would have to kick on over. So once again, we have what's the word we use to say that pi bond doesn't stay in place? We have a delocalized pi bonds. So remember, those are above and below the internuclear axis. However, do we actually alternate double, single, double, single, double, single? Is that reality? No, what do we really have? What is the actual bond order of all the carbon-carbon bonds? .5. Half the time they're double, half the time they're single. So in reality, they are 1.5. Okay. And it actually, experimental data shows that they are all of equal length, and their length is in between a double and a single bond, and the energy is between a double and a single bond. And this is such a common structure that very often, instead of drawing this whole thing, we will show it just each corner is a carbon. And we don't even bother showing the hydrogens coming off. Yeah? Sure, that's fine. Awesome, thank you. So each corner is a carbon. We don't show the hydrogens, and we can just show it going back and forth between single, double, and then reversing that. Or we get even lazier and we say that pi bond is delocalized. So guess what? This is our delocalized pi bonds. This bonding arrangement gives special stability to this molecule. The more resonance structures you have, the more stable things are, because electrons like to be spread out as much as possible. Yes? The more they can spread out to various places, the more stable it will be. So that's going to be important for next year. Here we go. Do you expect this structure to have resonance structures?
Would it be the same always?
You can't, because we go double, single, double, single, double. If this one kicked over here, then this would kick over here. Where the heck would this one go? Nowhere. Your homework, page, just do the exercises here, okay? And if you felt you didn't do well on your quiz, also study those, okay? Yes.
Right, mom.
There was like one, 2, 3 days, like tomorrow.